Good morning, students. Well, it's morning for me. It might not be morning for you. But anyway, welcome to Aqueous Reactions and Solution Stoichiometry, Part 2. Today we're going to talk about redox reactions, which are oxidation-reduction reactions. Remember that oxidation is the loss of electrons, and reduction is the gain of electrons. And the mnemonic device, I really did not make this one up. It's actually in your textbook. But the mnemonic device is Leo the lion goes grr. So Leo, loss of electrons, is oxidation. The lion goes grr, gain of electrons is the reduction. The other definition that you need is that the oxidation number is the charge. Remember, anything in red on this screen is something you should be writing on your reading guide that I gave you, or the notes. And finally, the last point here, read the rules for assigning oxidation numbers. They're listed on that page. Most of them, if you read through them, they should sound familiar. It's based on what we looked at last year, but there are a few little details that you want to be aware of. One of those is that oxygen is usually -2, but if you have a peroxide, such as the O2 2 negative, then that's going to be a -1. So O2, it looks like this, O2 2 negative. Actually, the oxidation number is -1. Hydrogen's always going to be +1, or at least most of the time, but if it is bonded to a metal, then it's -1. And the sum of the oxidation numbers of all the atoms in a neutral compound has got to be 0, whereas the sum of the oxidation numbers in a polyatomic ion should equal the charge on the polyatomic ion. So we'll do a little practice so that we clarify. All right, let's practice. Sample exercise 4.8 on page 140. So we have H2S. Hydrogen is always +1, so that means that sulfur has to be -2. S8. Well, the sulfur, when it's an atom in its elemental form, even though there's 8 atoms there, has an oxidation number of 0. And we have SCl2. Each of those chlorines is -1, so that's a total of -2. Sulfur has to be +2 there. Right, and then Na2SO3. Well, again, we know that oxygen is always -2, so that'd be -6. The sodium is always +1, so that'd be +2. So that means that that sulfur has to be +4. And finally, SO4, 2 negative. So each oxygen is -2, so that's -8. In order for the whole thing to be -2, sulfur here has to be +6. Notice that sulfur has taken on 5 different oxidation states here. All right, practice the next one on your own and then check back in. And we're back. So P2O5, this is -2, so that means that's got to be +5. NaH, here's the example of hydrogen combined with a metal. The metal here is sodium, always +1, so that means that hydrogen is indeed -1. Here is another polyatomic ion example. Each of the oxygens is -2, so that'd be a total of -14. In order for this to be -2 total, then this would have to equal +12. Chromium would have to be +12, so that means that each chromium is +6. SnBr4. Each of the bromines is -1, so that means that the tin is +4. And here is the final example of a peroxide. Ba is always +2, so that means that the total negative charge on the oxygen has to be -2, which means that each of those oxygens is actually -1, which is a peroxide. Good job. All right, now we're going to write the balanced molecular and net ionic equation for the reaction of aluminum with hydrobromic acid. So if we take aluminum in its solid form plus hydrobromic acid, and class, what is the rule for writing the formula of an acid? Well, if it's hydrobromic, that means there's no oxygen, so you're just combining hydrogen and bromine, and they both have a charge of 1, plus 1 and minus 1, so that is the correct formula. You don't need to add more hydrogens. All right, and what would be the products of this reaction? Well, it's a single replacement reaction, so you'd end up with aluminum bromide. Aluminum having a charge of plus 1 would be AlBr3 plus hydrogen. Remember, when hydrogen is by itself, class, what's that called? Yes, diatomic. All right, and then of course we need to balance this equation, so it would be 2, 6, 2, 3. And then we're going to write the complete ionic to eventually arrive at the net ionic. So here we have 2 aluminum, and these are solids, so they're not written as ions, plus 6 HBr. Well, that's a strong acid, so you're going to split that apart into its ions. That'd be 6H plus 6Br minus. Then we're going to split the aluminum bromide as well, because we would check our solubility rules and find that a bromide is always soluble. So that's 2Al3 plus 6Br minus plus 3H2. Remember to leave that unionized as it is a gas. All right, so then what do? Well, you can cross out whatever appears exactly the same on both sides. In this case, the spectator ion is the bromine. What is left is the net ionic equation. All right, practice exercise on page 142. You try it, and then check back in. All right, you're back. So we have magnesium plus cobalt 2 sulfate. And we're doing the same thing, writing the balanced equation and the net ionic. And Dan is having his breakfast. Mg solid plus cobalt sulfate, COSO4, aqueous. And you might say, well, what kind of reaction is that? Yes, you're right. It's another single replacement reaction. So we need to know, does the magnesium replace the cobalt? And we would determine that, yeah, magnesium is more active than cobalt. This does occur, so you're going to end up with MgSO4 aqueous plus the replaced cobalt, which is a solid. So, can you tell what the spectator ion is? So you would write Mg solid, again, not ionic. Cobalt sulfate, yep, that would be ionic, and that would dissolve in water, and so you'd end up with cobalt ion and sulfate ion. And over here we'd end up with magnesium ion and sulfate ion and cobalt solid again. So that means that the spectator is, yes, indeed, the sulfate ion. Now, just a word about whether reactions occur or not. On the AP exam itself, they're probably not going to give you one that does not occur, certainly not in the free response section, because that wouldn't make any sense. But there might be a multiple choice question that would relate to the activity series, so make sure you remember what that's talking about. Okay, more definitions. The concentration is the amount of solute dissolved in a given amount of solvent. Molarity expresses the concentration of a solution in moles per liter. What's the abbreviation, everybody? Oh, that's right, capital M. And so the practice exercise is on page 146, and we have 23.4 grams of sodium sulfate, so that's going to be Na2SO4, and we are to determine the molarity of that. So if I have grams, I need to convert it to, that's correct, you need to convert it to moles. So the molar mass of this is 142 grams in 1 mole. And now, if I'm going to get molarity, I need to divide by the volume expressed in liters, so that would be 0.125 liters. And if I multiply and divide, I should get 1.32 molar. Very good. Now try the next one and come back. Alright, so now we're going to do the practice exercise on page 147, and we are dissolving 5 grams of glucose in 100 milliliters of solution. So that's not molarity yet, but I know that I can get to moles from grams, and I can certainly get to milliliters from liters from milliliters. So first thing we're going to do is divide by the molar mass, which is 180. And then we are going to multiply by 1,000 because there are 1,000 milliliters in 1 liter. And if we multiply and divide, we get 0.278 molar. Notice I'm saying molar there. That's another common way of pronouncing the M at the end. So we have 0.278 molar. Alright, now we're going to try a preparation example. It says how many grams of sodium sulfate are required to make 0.35 liters of a 0.5 molar Na2SO4. So here we're going to start with the liters, 0.5350 liters. Although you could start with the molarity, it's still going to work either way. And then you're going to multiply that by the molarity because that will give you moles. And then what can we do once we have moles? Yes, that's right. You can multiply by the molar mass to arrive at the number of grams. And that would give us 24.9 grams of sodium sulfate. Good job. Next problem. Try it on your own if you like. Alright, so then it says, practice exercise on page 148. And we are looking at how many grams of sodium sulfate there are in 15 milliliters of 0.5 molar Na2SO4. So it's a very similar problem. We just need to convert milliliters to liters. You all should be pretty proficient at this by now. And then the second part of the problem asks for the volume of a 0.5 molar solution to give you 0.038 moles. So a slightly different problem. So the first one would be 0.015 liters times 0.05 or 0.5 molar times the molar mass is going to give us 1.1 grams of sodium sulfate. Notice here I only have 2 sig figs because of the 15 milliliters. Second part of the problem, 0.038 moles. And now I'm going to divide by the molarity because the moles need to cancel. So it's 0.50 moles in 1 liter. And then we want the answer in milliliters, so we're going to say 1 liter is 1,000 milliliters. And that's going to be 76 milliliters. Ta-da! So, dilution occurs when we add water to obtain a solution of lower concentration. Remember the verb is dilute, or actually that can also be an adjective. But anyway, here's the sample exercise, and you might remember the formula that we use. It's M1V1 equals M2V2, right, where M is molarity and V is volume. So here in this exercise we would just take 3.0 molar times the volume of that solution is equal to the 0.10 molar times the 450 milliliters. Note here that we can leave this in milliliters and just report our answer in milliliters. So V is equal to 15 milliliters. The tricky part with these problems is making sure that you get the ones together and the twos together. So that would be the answer to that problem. And let's try practice exercise on page 151. Right, and it says What volume of 2.5 molar lead nitrate contains 0.05 moles of Pb2 plus? And it continues on, several different problems here, so let's see what we can do. So first we're going to convert lost my place. We're going to convert the the moles, 0.05 moles, to liters by dividing by the molarity, which is 2.5 moles per liter, which will give us liters, and we're going to convert that to milliliters, which gives us 20 milliliters. All right, and then in part B, this is A, we have 250 milliliters times 0.1 molar equals V2 times 5 molar. So V2 then should be 5 mils. And finally part C, another dilution problem. 10 mils times 10 molar equals 250 mils times M2, leaving us an answer of 0.4 molar. Alright, so try those problems on your own, obviously, and check out my answers after you've tried them. Probably should have said that first. Alright, now we're going to put all this together. And so the first thing we're going to do is figure out how many grams are needed to neutralize 20 mils of 0.15 molar H2SO4. So you have to say, well, if we're neutralizing, then we're probably conducting a reaction. Well, the first thing I would need to do is, yes, you guessed it, write the reaction. So we have NaOH plus H2SO4. If this is neutralization, what does one of the products have to be? Yep, and that would be water. Putting in my coefficients a little early on you, sorry. And the other product, what's left? Well, that'd have to be sodium sulfate. Remember to write it correctly. That's going to be Na2SO4. And now we want to balance this thing, so we need a 2 in front of the NaOH in the front. So we are in search of the number of grams of NaOH. We have 20 mils of the 0.15 molar sulfuric acid. And so the first thing we would start with would be either the 20 mils or the 0.15 molar, but remember you're going to need the 20 mils expressed in liters. So we have 0.020 liters, and then we have 0.15 moles per liter. And this of course is the sulfuric acid. So now if we're doing a stoichiometry problem, what's the step that we must always include? That's right, we need to include the molar ratio. So now we're going to go to 2 moles of NaOH. Remember what you want, it's going to end up in the top. And what you started with is in the bottom, or the numerator and the denominator for my math friends out there. And then finally we're going to convert moles to grams using molar mass. And so we should get 0.24 grams of sodium hydroxide is necessary. Okay, that's part A of the problem. And part B, we are looking for how much hydrochloric acid would need to react completely with lead nitrate. So now we've got a different reaction. So we're going to write that. HCl plus PbNO32. Right, and what would we get from that reaction? Well, notice we're not getting water. This is not really neutralization. So this is more of a double replacement type of reaction where the lead and the hydrogen are going to switch places. So we'd end up with PbCl2. And you might say, well, how did you get 2 out of that? Well, you need to look at the charge on the lead in the lead nitrate. It has to be +2 there. So it's still going to be +2 on the other side. And then we have what's left over. Hydrogen and nitrate are going to combine to form nitric acid, which is HNO3. And now we need to balance. So we have a 2 in front of the HCl and a 2 in front of the HNO3. And then we would need to figure out what we have here. So we want to know the volume of this, and its concentration is 0.5 molar. And we have 0.1 moles of this. Right? And so then we would say that we need to know the volume of 0.5 moles per liter. That would result in 0.2 moles. And where did I get that 0.2? Well, check your stoichiometry, right? For every 1 mole of PbNO3, here we have 2 moles of HCl. So we need to make this, the answer should end up being 0.2 moles here. So it's X times 0.5. If we do the math, X is equal to 0.4 liters. Okay, last set of definitions here. Next week, probably, we're going to be looking more at titration. It's the process for determining the concentration of a particular solute in a solution. A solution of known concentration is called a standard solution. Remember, it's in red, so you probably need to write that down. Titrations can be conducted using acids and bases, precipitation, or redox reactions. Most commonly, we look at acid and base titration, but there are the other types. When moles of substances are equal, you have reached the equivalence point. We choose an indicator to show when the equivalence point has been reached. Your indicator is going to be a natural substance that has 2 different forms. So it might be one color in the presence of an acid and turn to another color in the presence of a base. And so as soon as we've passed that equivalence point, the indicator is going to change color. And when that happens, it's referred to as the endpoint. So the tricky part here is to make sure that your endpoint is actually occurring when you've reached your equivalence point. All right, thanks for watching.